Greetings and welcome to Distillate. In this video, we'll be discussing about thermodynamics in chemical reactions. So whenever we are talking about a chemical process, it is always accompanied by a chemical reaction. So let's say the chemical reaction taking place is something like this. A gives to B. All right. It's a very, it's basic, some example. It's random. All right. A gives to B. So if we have this particular reaction that takes place, so in that case, this reaction, it is going to affect the mass balance as well as the energy balance of the process, right? It is going to affect the mass as well as energy balance of the system. So obviously mass balance, because there is a decrease in the number of moles of A and there is an increase in the number of moles of B. So naturally, there's going to be a change in mass and mass balance. And there's going to be a change in energy balance as well because of something called heat of the reaction, which we'll actually be discussing over here. So because of that, there's going to be a change in the energy of the system. There is going to be release of heat, or there is going to be consumption of heat, something of that form. So in that case, this particular chemical reaction would also be responsible for affecting the energy balance of a particular system. So when we discuss about thermodynamics of chemical reactions, so we have to consider both mass and energy balance, while our more of our focus would be on energy balance, on heat of the reactions and calculations of heats. All right. For mass balance, which whatever the mass changes take place while we are dealing with chemical reactions. So mass balance that involve chemical reactions, they have already been covered in chemical process calculations. So we'll not be taking up this part over here. So thermodynamics in chemical reactions. The first and the most basic term over here is heat of the reaction. So we must keep in mind that most of the chemical reactions that take place are generally at constant pressure. All right. They are generally they generally take place keeping the pressure constant. So when you keep the pressure constant, so in that case, heat actually becomes equal to enthalpy. We have already discussed this thing in the past few videos, that heat becomes equal to enthalpy at constant pressure. And if that's the case, then heat of the reaction actually becomes enthalpy change during the reaction. All right. It becomes the enthalpy change that takes place during the reaction. And hence, we call this heat of the reaction as the enthalpy change. So enthalpy change that is taking place in a particular reaction, let's say the reaction is reactants to products. So in this case, the heat of the reaction would be equal to enthalpy change, which is the enthalpy of products minus enthalpy of the reactants. So this is the way you are going to calculate enthalpy change of a particular reaction, or you can say the heat of a reaction. So for example, if I take a very simple chemical reaction, A plus B gives C plus D. So in that case, we'll be having enthalpy of products equal to enthalpy of C plus enthalpy of D. While when we're talking about enthalpy of reactants, so that is going to be enthalpy of A plus enthalpy of B. All right. So these two are going to take place. These two are basically calculated from the reaction. And finally, we'll have the heat of the reaction, which is delta HR, is equal to enthalpy of products minus enthalpy of reactants, which is equal to HC plus HD, which is products, minus HA plus HB, which is enthalpy of the reactants. All right, so that's how you calculate the heat of the reaction. Then we move on to standard heat of reaction. So when we talk about standard heat of the reaction, so it is basically the heat of the reaction when the products and the reactants are both at standard state. Now, how to determine the standard state? To determine the standard state, we have to specify the pressure, temperature, composition, and physical state of the species. So by convention, what we do is we take standard pressure equal to 180 and we take standard temperature equal to 298 Kelvin. Okay. And when we talk about the physical state, so it is the state of the substance at standard temperature and pressure, that is at 298 Kelvin and 180. All right. So for example, carbon in its standard temperature and pressure is solid in nature, while oxygen is gaseous and water is liquid. So these are their standard physical states. All right. So if I have carbon as solid at 298 Kelvin and 180, so in that case, this is actually at its standard state. All right. This holds quite a lot of importance when we talk about some substances like, for example, water. So as we know, water can exist in both liquid as well as in vapor state or in gaseous state, right? So since water can exist in both the states, so let's say if I have temperature equals to 298 Kelvin and pressure equals to 180, and somehow using some mechanism, we find that the reaction has water released in its gaseous state. So in that case, we'll not consider this as the standard state. This is not going to be the standard state for water. We'll only consider it as the standard state for water if water is in its liquid state. All right. If water is in its liquid state with temperature equals to 298 Kelvin and pressure equals to 180. All right. So that holds quite importance. All right. So when we discuss about standard heat of reaction, we denote it by delta H naught at 298. 298 is basically denoting the temperature and naught means standard heat of the reaction. All right, standard heat of the reaction. So that's delta H naught 298. That's how you denote a standard heat of the reaction. Okay. Now let's talk about exothermic and endothermic reactions. So let's say we have a particular reaction. Let's say reactants give products. All right. So the first case may be that this is an endothermic reaction. Now we know that for an endothermic reaction, heat is released. Okay, heat is released. So now what will happen? Let's say we have a reactor over here. We have a reactor and we are feeding the reactants to this reactor. And let's assume that all these reactants have been converted to products. All right, all these reactants have been converted to products. There is no reactant, no traces of the reactant found in the product stream. All right, so that's there. And then since it is an endothermic reaction, so we are going to say that some heat will be released. Let's say approximately 200 joules of heat is going to be released. So that 200 joules is going to go out, right? The 200 joules of heat is going to go out. Now, once we have this block diagram, we can simply make an energy balance equation as HR, which is enthalpy of reactants, is equal to HP plus 200. All right. I'm so sorry. In case of exothermic reaction, heat is going to be released. If it is an exothermic reaction, then the heat is going to be released. Endothermic will consume heat or it is going to absorb heat. So yeah, coming back, if it is an exothermic reaction, heat is going to be released. So let's assume that 200 joules of heat is being released. So in that case, we'll have by the energy balance, heat input, which is HR, is equal to heat going out of the reactor, which is HP, enthalpy of products, plus 200 joules. So in that case, heat of the reaction, delta HR, is HP minus HR, which from this equation, we get it as minus 200, right? HP minus HR is equal to minus 200 joules. Now, As you can see that for an exothermic reaction, we have got this heat of the reaction as negative. So if heat of the reaction is negative, then it is an exothermic reaction. All right. This is a way to prove this particular fact. And then the second case which we might take for this particular reaction is that it is an endothermic reaction. So if we take it to be an endothermic reaction, we'll say that heat has been consumed. All right. Or basically this heat is going to be given as input. So let's say this is the reactor. Same conditions, we have reactants, all completely pure reactants, and all of it has been converted to P. And now, since this time we have an endothermic reaction, therefore we are going to supply 200 joules from this side. So an energy balance would give us HR, which is enthalpy of reactants, plus 200 gives you HP. So in that case, heat of the reaction is going to be HP minus HR, which is equal to 200 joules. Now, as you can see, this is positive, and this can actually be very well explained over here that heat of reaction, if it is positive, then it is an endothermic reaction. So these two are one ways to prove that the heat of reaction for an exothermic reaction is negative and the heat of the reaction for an endothermic reaction is positive. All right. Also, for an endothermic and exothermic reaction, if we talk about an energy diagram, all right, if we talk about an energy diagram, or in short, if we make it an enthalpy diagram, right? So on the y-axis, we are going to have enthalpy, and on the x-axis, we are going to have progress of the reaction, right? So it is always seen that for an exothermic reaction, you'll always find that since the heat of the reaction for an exothermic reaction is negative, therefore HP is lesser than HR. All right. So you'll actually find HR somewhere here because HR is greater, and HP would be found somewhere here. Now, as you can see that HR is at a higher energy state while HP, or you can say the product, it is at a lower energy state. Therefore, in order to move from R to P, or basically from a higher energy state to a lower energy state, it is required that some heat is released. Okay, some heat is released. So that is why we see that for an exothermic reaction, heat is released. All right. And over here, as you can see, since HR is greater than HP, therefore, definitely it's going to be one of the conclusions that for an exothermic reaction, the heat of the reaction is negative. At the same time, if we talk about an endothermic reaction, so for an endothermic reaction, we know that heat of the reaction is positive, which means HP is going to be greater than HR. So you'll find HP somewhere here in the energy diagram and HR would be somewhere here. Now, in order to move, since we have to take R to P, therefore, in order to move from a lower energy state to a higher energy state, we need to supply heat. So therefore, an endothermic reaction requires heat. You need to supply heat to an endothermic reaction. All right. So in short, you'll always find that for an endothermic reaction, heat of the reaction is positive, while for an exothermic reaction, heat of the reaction is negative. All right. Now, we come to some special cases of heat of the reaction. Correct. So if the reaction that is taking place is a combustion reaction, all right. So let's say if I'm talking about combustion of methane, all right. So we have CH4 plus oxygen gives CO2 plus water, all right. And okay, two. Yeah. So this is the combustion reaction for methane. All right. So if we find the heat of this particular reaction, then that is actually equal to heat of combustion of methane. All right, it is heat of combustion of methane. So remember that if the chemical reaction taking place a is a combustion reaction, then heat of the reaction is same as heat of combustion. All right. Now, we already discussed this part while we were dealing with application of material balance to combustion. But let's once again go through this part. So, combustion reaction, as you can see, all combustion reactions, they follow the production or the formation of water. All right. Now, water, it can be formed in either liquid state or in gaseous state. All right. It can be formed in liquid state or in gaseous state. And we all very well know that combustion reaction is an exothermic reaction. Heat is released in case of combustion. All right. So since it is an exothermic reaction, so delta HR is definitely negative, which implies that we'll have HP lesser than HR. Correct? HP is going to be lesser than HR. Now, the greater is the difference between HP and HR, the lesser is the heat of the reaction, right? If there is a greater difference between HP and HR, let's say if you have HP equals to 200 and HR is equal to 100, then in that case, the heat of the reaction, sorry, HR is equal to 300. Then in that case, the heat of the reaction is going to be minus 100. That means 100 joules has been released. 100 joules of energy has been released. But at the same time, if we take HP is equal to 250 and HR same as 300, then in that case, delta HR is equal to minus 50. So this has to be, the greater is the value of HP, the lesser is going to be the heat of the reaction, right? So that means if HP is high, then less amount of heat is going to be released. If we apply the same concept over here to, let's say, the methane reaction. So in the methane reaction, the heat of the reactants, it basically is summation of enthalpy of CH4 and oxygen, right? That's not going to change. That's not going to change. When we talk about products, so in products, we have enthalpy of carbon dioxide while enthalpy of water. All right. Now, if we have water in the liquid state, then it has a lower enthalpy. While if we have water in gaseous state, it has a higher enthalpy, right? It has a higher enthalpy. So if water is found in gaseous state, then in that case, HP is going to be higher. So if HP is going to be higher, delta HR, or you can say the magnitude of delta HR is going to be lower. All right. While if HP is lower for the case of liquid, when water is found in its liquid state, then in that case, the magnitude of heat of the reaction is going to be higher. So based on that, we can actually say that if we are talking about a simple combustion reaction, then if water is formed in its liquid state, then in that case, heat released is greater. All right, because the heat of the reaction has a greater magnitude. While if water is formed in the vapor state, then heat released is lesser, and that is why, because the heat of the reaction is lower, the magnitude of heat of the reaction is lower. So if water is formed in liquid state, then in that case, we call if water, however, is in vapor state, then in that case, the heat of combustion is known as the net calorific value or net heating value. And as we already discussed, that GCV, which is for water in its liquid state, is going to be higher, while NCV is going to be lower than that. All right. So that's how we define HCV and NCV, or GCV and NCV. All right. Then we come to another type of heat, which is heat of formation. So again, if the reaction that is taking place is a formation reaction, for example, let's say carbon dioxide formation reaction. All right, if we are talking about a carbon dioxide formation reaction. So the heat of formation is going to be equal to, basically heat of the reaction is going to be equal to the heat of formation. Okay. So heat of formation is the heat of the reaction, then 1 mole of a substance. This has to be kept in mind. So if we have to find the heat of formation of this reaction, then in that case, we have to keep in mind that carbon dioxide has to be 1 mole. Okay, only then the heat of the reaction is same as heat of formation of carbon dioxide. If the reaction is something like this, then since this is the whatever is going to be the heat of the reaction, that is going to be heat of formation for 2 moles. So that cannot be categorized as a heat of formation. It will simply be a heat of reaction. All right. So the heat of formation, if a particular reaction is taking place where 1 mole of a particular substance is being formed, then in that case, that heat of the reaction is heat of formation of that substance. All right. So you have to keep in mind that in such a reaction, you will have only one product. You will have only one product, and that product will have only 1 mole being formed. Okay. In that case, the heat of the reaction is going to be heat of formation. All right. So heat of formation of all elements in their standard states is arbitrarily assumed to be 0. All right. Heat of formation of all elements in their standard states is 0. All right. For example, carbon is solid in standard state. We discussed earlier. So enthalpy of formation of carbon solid is 0. Similarly, oxygen is gaseous in standard state. Hence, oxygen gaseous is 0. Enthalpy of formation of liquid oxygen, however, would not be 0 because liquid oxygen is not in its standard state. Okay, in its standard state. So if I give you this particular reaction, then in that case, you can simply say that, okay, since this is in its standard state, this is in its standard state. Therefore, we are going to say that enthalpy of reactants is equal to 0. All right. However, if I give you the reaction as this, then in that case, you cannot say so because this is not in its standard state. All right. Also, this rule does not apply on compounds. There is a difference between elements and compounds. Elements are made of a single atom. All right, single type of atom. For example, OO. All right, this is made up of oxygen, so it's going to be an element. Okay. However, CO2 is a compound. So however it is gaseous in standard state, the enthalpy of formation of CO2G is not 0. All right, keep in mind, although in its standard state CO2 is in its gaseous state, however, enthalpy of formation of CO2 as gas is not 0. All right, there is going to be some enthalpy of formation for CO2. These rules, these laws that we define, they are going to be very useful when we'll be dealing with further calculations of heats of reactions, and we'll be combining a lot of equations all together. So in that case, it's going to be very useful. So these are the two types of heats that we've discussed: heat of combustion and heat of formation.